Is, and this is going to relate pretty specifically to what we do today. So it seems like it's maybe an out of left field question or something like that, but I promise it's going to work for you today. What is a dozen is the first question. So I'm just looking for a number that represents a dozen. When you say a dozen, it really means a number, correct?
Yeah.
What's the number that it means, Stacy? All right, dozen means 12. Everybody knows that, right? That's just one of those standard things in life, like you don't get told, you just kind of figure it out. If you go down a little further, or read a little further, it says, what is a score? And as it relates to a number. This one's a little trickier. This one you would have had to learn. You just don't learn it or know this because people don't talk about it anymore. Jasmine?
I'm not sure if it's 100 or 50.
No, not that. Jason? 20 years is a score, yeah. So when it talks about 4 score, you know Abraham's famous, that's the Emancipation Proclamation, or that is the... Oh, that's terrible. I can't remember that. Yeah, it's a very famous speech, which I can't recall right now. But in that speech, 7 years ago, 4 score, each score is 20 years. So how many years is 4 score? 80 and 7, so 87 years. 4 score and 7 years ago. That means 87 years ago, our forefathers set forth on this. So, next question had to do with how many beetles are there in 2 dozen beetles? Shayla? All right, and what about 10 dozen beetles? 120. So it's simple. So when we talk about it in terms of scores, Rylan, can you thank you. When we talk about it in terms of score, when we talk about it in terms of dozen, everything's good, right? Like if I say, how many are there in 10 dozen, you know it's 120. How many are there in 5 dozen, you know it's 60, right? Because a dozen just represents a number. It's like a short way to say a number. So I'm going to teach you a different word today, a word today that represents a number that is absolutely humongous. So we're going to use a number that's humongous, and we use a word to represent it that's going to make your lives much easier instead of having to use that number every single time, okay? So that's why we went over this. So we're going to keep this in the back of our head here as I come around and check off the homework that you have. So on page 50 today, your topic is still balancing reactions, and then your essential question today is right there. How do you convert moles to mass and vice versa? So we're beginning the topic of a mole, and the word mole is very similar to the word dozen. As in, when you've got a dozen of something, you've got a number of something, right? You've got 12 of something. When you've got a score of something, you've got 20 of something. When you've got a mole of something, it's an unbelievably big number. Have you guys ever learned scientific notation? How to write really big numbers with scientific notation? All right. So I'm going to do one thing with you then and show you how big a mole is in terms of numbers. So just like 1 dozen, right? 1 DZ equals 12, and 1 SC, 1 score equals 20. 1 MOL is how you abbreviate it for mole, equals a huge number. It is 6.022 times 10 to the 23rd power, which means this. You want to, if I would write down that number, but if you want to see what it looks like as like a real number, that is 6.022, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18, 19, 20.
Is there a decimal anywhere in there?
Nope. That's that number.
How many zeros is there?
A lot.
23. A lot.
I don't.
There are 23 up there.
Nope, there are not 23 zeros.
I just said it was 13.
It's not 13 either. Wrong on 2.
Yeah, I said it was 5.
Zip it. Yep. So, this number, this is hard to get unless you're going to focus. So if you're going to mess around, it's going to make it hard. I can promise you that. It's as hard as you need it to be to understand this stuff. 1 mole is equal to 6.022 times 10 to the 23rd. That's a number, right? Just like 1 dozen was equal to 12, 1 score is equal to 20. 1 mole is equal to that number, and it is a huge number. It is that many, and it's used in reference to atoms because atoms are really small, so we needed a big number to kind of make them realistic. So we use this number as a mole, 20. Yep. So as you look at it, to give you an idea of how big a mole is, if you had 1 mole of popcorn kernels, you know, it's like on popcorn kernels, and you had them over the United States, and they covered the United States, you'd have a layer that was 256 miles thick of popcorn kernels if you had just 1 mole of popcorn kernels, to give you an idea of how big that number is. It's huge. Yeah, it's unfathomable, right? I mean, you could never count that high. You could never do anything. So we've got to come up with some stuff for it. Jasmine?
You said there's 20 zeros, there's only 7 I found 8. Who cares?
Problem solved.
Thank you.
Did I see another hand up somewhere? Same thing. Okay. So that number we can use, and we're going to use this version of it when we do this, stuff. So that times 10 to the 23rd, when it's times 10 to the 23rd, that's just telling you to move the decimal over 23 times to the right. If it were times 10 to the negative 23rd, it'd be telling you to move the decimal that 23 times to the left. What's that? Yeah, that'd be a really, really, really small number. So we're going to use this today to help us out, because I've only taught you one thing about the periodic table, about that number on the bottom, like the mass number that we've been using, right? We said that when you have 1 thing of potassium, it weighs 39.09 grams, right? So what we're going to learn about that number today is this. It actually serves a dual purpose. When you have one, up there, it's when you have 1 atom of it, it weighs that much in atomic mass units, right? We said each proton is 1 for atomic mass unit. Harley, can you sit on a chair, please? Thank you. Each neutron weighs 1 atomic mass unit, and electrons weigh like 1/2000th of a mass unit. So when you've got exactly this many atoms of any substance up there, like lithium or beryllium or anything like that, when you've got exactly that many atoms of it, it weighs exactly that many grams. So if you've got 1 mole of lithium, it weighs 6.941 grams. If you've got 1 mole of vanadium, it weighs 50.942 grams. So if you've got exactly that many number of atoms there, that's how much it weighs. That's what that's a reference to. And using that, we're going to do some work today on the paper you grabbed when you came in. So we're going to convert from mass to moles and moles to mass back and forth, because we can do that. And I promise you, it's not bad at all, as long as you've got a periodic table that you've got masses on and a calculator or a cell phone with a calculator on it. We can make this work. So a mole ratio is the ratio of moles provided in the problem to the moles desired in the problem. That's one of the ways we can use a molar ratio to solve our problems today. That's one of the options. The other option we can use is we can just balance them with new numbers. Either way works fine. The molar ratio is a little simpler way to do it. To do molar ratios, you got to know like the cross multiply and divide thing with fractions. Do you know how to do that? If you don't, I'll teach you. But it really does make life a lot easier. So in this problem, if we're back... Sorry, Sheila. So in this problem, we're back to number 1 here. It says a molar ratio is the ratio of moles provided in the problem to moles desired. So if we look at the problem, it says calculate the number of moles of oxygen gas that would react with 5 moles of C3H8. So we're looking for a ratio between what's given and what is wanted. So in this ratio, would you agree that it says calculate the number of moles of oxygen gas? So that's what we want. It's telling us to calculate the amount of oxygen gas that would react with 5 moles of C3H8. So that's what we're given. So we're going to set up a ratio of what's given to what's wanted. So here's how that ratio looks based on this balanced equation. This mole ratio comes from the balanced equation. So if you look at the balanced equation that is there, you can see that the ratio of C3H8, what's the coefficient in front of C3H8? Nope. Nope. Nothing. So it's a 1, right? So of C3H8, what is the coefficient in front of oxygen? 502. So that's our molar ratio that we're going to use right there, the one that's given to the one that's wanted. On this side, we're going to do the same thing, C3H8 to oxygen, like that. Sorry, I'll stop. Go ahead.
Okay, why is it not in the center of the line?
Oh, over, because we're going to put numbers there.
Oh.
I'm just leaving a blank spot for numbers. So in that problem, it says it wants to know how many are going to react with 5 moles of C3H8, right? That's what it gives us is 5 moles. So we know that 5 is going to go here, 5 moles of C3H8. The ratio is 1 mole of this to 5 moles of this. Now it's telling us we've got 5 moles of this, and we've got to figure out how much oxygen that's going to be. The official way to do it, some people can do this in their head too, but the official way to do it is to cross multiply. So if the numbers are like diagonally across from each other, like 5 and 5, that means you multiply them. So that's a multiply thing right there. That's my best multiply symbol. And then this way is a divide. So it's always multiply first and then divide second. And this one it doesn't matter because there's a 1 there, but it's always cross multiply and then divide. So far so good? Okay. And when you do that, 5 times 5 divided by 1 gets you. Go ahead, Shayla.
Is that only if the numbers are the same?
Nope. Always going to be cross multiply and divide every single time. So the answer to this problem is 25 moles of oxygen is what it's going to take. That's one way to solve this problem. The other way to solve this problem is like this. You can set up the problem. C3H8 plus O2 turns into CO2 plus H2O. And you can balance it with the information they give you. Because they say they're giving you 5 moles of C3H8, right? So you know this is a 5. And from that, you can figure out the rest. We'll see we'll get the same answer either way. How many things of carbon do we have right there? 15. All right. So how do we make there be 15 on that side of it? How do we make there be 15 right here? Yep. You're going to need a 15, right? So now we're good there. How many things of hydrogen does that give us right there? 40. How do you make there be 40 hydrogens right there? Nope. 20. And then the last bit, because we always save oxygen for last, how many oxygens do you have right there? 30. And how many do you have right there? 20. What's 30 plus 20? 50. How do you get 50 right there? So either way, you come up with the same number for oxygen. It's just this way tends to be a little easier. You can do it either way. You're going to get the same answer either way, but that's the simpler way to do it. Question, Gage? Okay. So far so good there? Okay. Next step, it says part B, determine the mass of the oxygen in the problem. So how many moles of oxygen do we have? Okay. How do you figure out how much 25 oxygen went? Yep. Do the same thing that we were doing yesterday in the homework that we just went over. So that number for oxygen should be 16, I think, if you look on your periodic table. So all you'd have to do is this times 16. Should come out with a pretty even number since it's 16 times 25. 25, because we're already measuring. I'll show you what we're talking about here. We've got 25 things of O2, right? So really that's how many oxygens? 50. So it'd be 16 times 50, which... Yep, grams. And that's how you solve these things. That's all there is to these things. So this is real, like we're kind of advanced beyond the other freshman classes at this point. The other freshman classes aren't doing this. Because you guys are good at this stuff. So we're kind of this is going to make your life easier when you get to chemistry. So we're kind of... So number 1 is done, which means we're on to number 2. Shayla? Okay. Questions, Alexis? Like I said, if you're thinking them, ask them, because if you're thinking it, there's probably 5 other people thinking the same thing you are, and they're just not comfortable asking it.
Okay, what about the
Go ahead. Okay. We can work that out with a little, confusion gets cleared up with repetition, so we can fix that for you. Cool?
Wait, where did the coefficient create the CO2 go?
Coefficient for the CO2?
Yeah. Or like it's like free CO2. Where did that go?
What do you mean where did it go?
15. Oh, wait. But in the top equation, I was.
Gotcha.
Yeah.
So that's a balanced equation that was on top, right?
Yeah.
Okay. And then down below, it said we're not starting with whatever the 1C3H8, right?
Yeah.
It says we're starting with 5. So we've got to rebalance it as though this number is 5 and can't change. So that's why everything else is kind of weird. So if it were in its lowest possible terms, it would be that 3. But it's not in lowest possible terms because we're starting with a different number here. So this will kind of come together as we do the next one, I think. Yeah, we'll get there. I promise we'll get there. So number 2, it says in the following reaction, and this one you're going to have to write out on your paper. So would you write out the chemical reaction on your paper so that we can make this happen? So we need a little practice with that too. But it says in the following reaction, 2 moles of aluminum and iron nitrate, I think, react to yield 2 aluminum nitrates and 3 irons. Calculate the number of moles of FeN2 that would react with 4 moles of aluminum. So when you write this thing out, right, it tells you right away that 2 aluminums, so 2 Als, react with Fe3N2 plus Fe3N2 to turn into Al. How many? 2 AlNs plus Fe, and that's a 3. So if you've written your thing out, that is it. That's your balanced chemical equation right there. It's given you in the problem. So far, so good? Jasmine, are you good with that part? Shayla, are you good with that part?
Wait, how do you get that out?
Yep. Did you read it?
Yeah.
Did you try it? So you're going to have to try doing these in order for it to work out for you. Because if you don't try it, you know what I mean? Yeah. All right. So we're working with this problem. It is balanced the way it is. If you look, everything's balanced out. And the question for it says, calculate the number of moles of FeN2 that would react with 4 moles of aluminum. So we've got to set up our molar ratio of aluminum, or FeN2 to aluminum. So our ratio is going to be FeN2 over aluminum, and it's going to be the same over here, FeN2 over Al. Do you guys see where I'm getting those things from? Don't need them just yet. I'm just putting in the chemical labels now. We'll get that 3 in just a second. Here, that's an L for aluminum. So I haven't put any numbers in yet intentionally because all I'm doing is setting up the ratio of the thing we are provided with and the thing that we want. So it tells us that we've got 4 moles of aluminum, that's the thing we've got, and that we want 3 mole, or we want a specific number of moles of FeN2. So I haven't put any numbers in. I've just put the 2 chemicals that we're worried about in there. That's the only thing, that's the only step.
What about 3 in the subscript?
Oh, I forgot that.
Yeah, the others.
Sorry. I thought you meant what happened in the 3 out here. My bad. Yeah. Thank you for that. Sorry for the confusion that may have caused. Trinity?
What if it's FE3 and 2 on there, wouldn't it be FE3?
Yep. Thank you. I'll get it one of these days.
One day.
Yeah. So now we're set up, right? Does everybody understand why we're using these 2 chemicals on top and bottom? What's that? Okay. Next thing, hey Shayla, it helps if you hey. Huh? Negatory. So as you're looking up here, it does not matter which one's on top and bottom as long as you've got it the same on both sides. So don't worry about which one goes on top and bottom, but if you put aluminum on top, make sure it's on top on this side too. So you don't have to worry about this is the only one that can go on top or this is the only, it doesn't matter. As long as you've got the same one on top. Does that clear stuff up a little bit for you here? Yeah. Okay. So next thing, we're going to plug in the given ratio of moles to moles. in the balanced chemical equation, how many moles of FeN2 do we have? Gage? How many moles of FeN2 do we have? What's the coefficient of FeN2? If it's blank, it's a 1. Very good. So, no problem. And then, what is the coefficient for aluminum here? 2. So that's our molar ratio right there, is 1 to 2. You guys see where I came up with that? Yeah. Anything I can clear up or more support I can provide to get that for you? Hold on. 2 questions at once. Tanya, go first, please. Because that's its coefficient right here. That's where that number came from. Trinity?
But in the thingy, it says Fe3N2 that would react with 4 moles of aluminum.
Yep, that's going to go. So this is the given side. I'll put a G over here for the given side. And this is the side we're trying to figure out. So we're given, like this is from the equation here. And then we're going to try and figure it out on this side. So in that thing, it says that we are given 4 moles of aluminum, right? So that goes here. So the unknown one goes on the right-hand side. And now we can figure this out. We do the cross-multiply thing. The numbers that get multiplied are diagonal from each other. So right there, 4 times 1 gets you 4. And then you divide by the number that's left over. So there's the multiply thing right there because they're diagonal. And then you divide by 2. So 4 times 1 is 4. And then divided by 2 is 2. So there's our answer right there to that question. Okay?
Where does 4 come from?
Gotcha. In the problem, if you read it, it says, calculate the number of moles of FeN2, which is this, that would react with 4 moles of aluminum. So there's our 4 right there.
Oh, okay. Never mind.
Cool? That's not part of this. That's not part of what we're trying to find out. Nope. So hold on one second. So Cole asked the question, what happened to the ALN that was out here? And that you could be asked to solve for that, in which case that would be part of your ratio, and we'd leave the other one out. But in this one, we're only dealing with these 2 things. So our ratio just concerns these things. So we don't even have to worry about that. Yep. The only ones you have to put in the ratio are the ones that are provided to you in the problem. Like, here's what you got, here's what you're trying to find. Cool? Cody, you had your hand up too. Okay, how can I help? Okay. Did you see where it came from? Okay. And once you have the 4 down, so if we start here, do you know how to get the numbers on this side? No, forget about this. Do you know where this 1 and this 2 came from? Yep, so left side comes from the balanced equation every single time. Right side is the side that's given to you in the problem. So we're given 4 aluminums, and then we've got to figure out what that is based on this ratio. Okay. So the other way to do it, we said you can also do it with like a balanced equation. So you can use the molar ratio way, or you can use like a balanced equation way. And it says in this that you're provided with 4 moles of aluminum, which is right there. So if you do it the balanced equation way, you start this way, and you've got 4 moles of aluminum there, which means you would have 4 moles of aluminum here. How many things of nitrogen does that give you? 4. So here, how many things would you have to get 4 of nitrogen? You'd need a 2 there, which is exactly what we came up with. And then that gives you how many irons? 6. So you need a 6 there. So either way you do it, you come up with the same answer. It's just that the molar ratio saves you a little bit of work, I think. Some people prefer to do it this way, and that's fine too. Whichever is easiest for you, it really has no bearing. I'm not going to judge. So far so good there? Okay. And part B is the same thing you were doing yesterday. Determine the mass of the FeN2 used in the problem. And if you had this many moles of iron nitrate or iron nitrite, whatever it is, how much would it weigh? So that's your part, because I know you guys can do that. Figure out how much mass that has. Let's give everybody a chance to figure it out. Mass on number 2, we wanted to figure out how much 2 moles of FeN2 ways, and if you're close, you're doing it right. Remember, you just kind of maybe rounded wrong. So Trinity says she's got it.
Oh, I got 392 grams.
I got slightly different than that, which means that's a rounding issue.
390.8.
High five. 390.8.
Look at that. If you are not doing your numbers,
Here's all right.
FE should be 56 because 7 months 5 to.
Whoa.
We know.
We're rounding to 1 decimal place, right? So FE rounds to 55.8.
But if you round your numbers right, it should be 7 bumps the 4 up to a 5.
How do you round to the 10th spot? You got to look at only the one that comes right before it.
That's not how they teach us in math.
So think about it. And we're on number 3. If you feel like you got it and you just want to try it as I'm doing this up here, go ahead and move ahead at your own pace, and you can always check back in and see what I'm doing. But I'll do this one up here with people that want to do it with me. So for number 3, first thing you got to do is write out the balanced chemical equation. And that is 4H2O plus 7CO2 react to yield C7H8 and 9O2. So, if you're following along, Carissa, and you're writing the chemical equation, that is the proper chemical equation for this one. It's basically I don't even know if that chemical equation can happen. It's the opposite of a combustion reaction, but that's the chemical equation that's there. And remember, if you want to move ahead at your own pace, feel free to move ahead at your own pace here. Kind of. So it says calculate the amount of moles of C7H8 that would form if 27 moles of oxygen form. So the two elements, or the two compounds, our molar ratio is going to be between oxygen and C7H8. So we're going to have, doesn't matter which one goes on top, remember, it can be O2 over C7H8. Yeah?
Can you explain how you set this up, because this is the part right here.
Like this part?
No,
This part?
Yeah.
Gotcha. No problem. So if you read the problem number 3, after the period it says calculate the amount of. Yep. You see where I'm looking, Shayla?
Yeah.
Okay. Calculate the amount of moles of C7H8. So we know that's going to have to be part of our ratio. So let's put it on top. It doesn't matter if yours is on bottom already, whatever. So we're going to go C7H8. And then it says, after it says that would form if 27 moles of oxygen were formed. So the other one we're going to have to use is going to be oxygen. Doesn't matter if you've got one on the top and one on the bottom. As long as they're the same on this side, then you're good to go.
So, on all the equations, it's going to tell us how to write it?
Yep, it's going to be right there. That last sentence will tell you what the things are in the molar ratio. Right?
Yeah, why would you put a 27 in front of the O2 though?
We're going to, so hold on just for now. So the first thing we got to do, this is the side that comes from the equation, right? Is set up the molar ratio. How many moles, what's the coefficient in front of C7H8? 1? Yep. What's the coefficient in front of oxygen? 9. So that's our setup. In the problem, as you read it, it says 27 moles of oxygen are formed, right? So that's going to go over here. And then we're going to solve for this. Yep. So 27 times 1 divided by 9. 3. So you can do it that way, or this one's really tough to do it like the balanced equation way and put a 27 there because oxygen's in 2 places on this side. So the molar ratio is just way easier on this one. But that's your answer. And then it says figure out what 3 moles of this stuff would weigh. So when you figure out what 3 moles of this stuff would weigh, how many carbons do you really have there? 21 carbons. So 21 times C. How many hydrogens do you have there? And that's it. Add those together and you're there. This is a perfect time for me to talk to you about my new invention. It's a periodic table calculator. Yeah, so it's a calculator you can put on your smartphone. So instead of having to look to see what carbon's number is every single time, you can just go 21 times C, and it's done.
That's actually a really good idea.
I know.
But
You're welcome.